Okay. So we are going to redo all of relational algebra in less than 5 minutes. But remember that relational algebra is not a programming language. So I really don't care if you put a string with quotes or without quotes. It's not really important. We are not doing data type, float versus integers. It's not important. What's important is the logic. And the thing that we really care about is the schema. So what attributes refer to what columns of the table. So often that's the main thing we care. If you think about it, we don't even care about the names of relations other than understanding what is input to a relation. But the names of relations is even irrelevant. What we do care is what attributes are in the relations. So we've learned basically very simple operators. The set operations require that you have two relations with the same exact schema. So R and S must have the same schema. If not, set operations are not defined. So given R and S with the same schema, you can find tuples that are in both R or S, right? Not exclusive or R or S or both. And when you do set union, remember that this is a set of tuples, so there are no duplicates. So even if you had duplicate tuples, the same tuple in two relations, when you union, obviously you're going to only have one of it. So remember, set of tuples, no duplicates. We learned that you can subtract one relation to another, so it's all the tuples in R that are not in S, right? We said this is useful because this is the only way we do negation. Generally, when you want to find something that is not true in the database at all, you use a set subtraction. And we have intersection, which is not technically required, but is very useful. It's the tuples that are in both relations. Then we learned about selection. Selection applies to a single relation. So we write it with a sigma C of R, where C is a Boolean condition over attributes of R, right? So select all tuples from R that satisfy the condition C. And that condition C refers to a tuple at a time, okay? So C is a condition over attributes of R and R only. Okay, I will tell this over and over, but you will write conditions that does not satisfy this, but that's a learning process. Okay, projection is the reverse. Selection is the slice. Projection is dice. That you are going to keep all the tuples, but you're going to only keep some of the attributes. So you're going to do pi of a1 through an of R, means that return all tuples, but only attributes, and only attributes a1 through an. Right? Now, after projection, you may end up with duplicate tuples. Then, of course, they are removed because this is a set of tuples. By the way, when you're writing homework and you don't want to learn LaTeX, it's perfectly fine, and you don't want to figure out how to do these symbols, which is okay, you are computer science students, right, for the most part. You can, a lot of the editors, you can find these easily in the special characters part. Even you don't want to do any of that, I am perfectly okay if you actually spell out. So instead of this, you can just say R union S. Instead of this, you can say select C from R. So you can have shortcut for these. I don't care that I have the Greek symbols. but I feel like you should be able to figure out how to do that. But if you don't want to use LaTeX, you can still type it in a readable way, as opposed to kind of handwritten, which is much harder for your kids to see. Okay, so select project, and we did renaming. Renaming is just basically being able to change the names of the attributes. We learned different methods. I personally like the one where you rename all the attributes like this. It's just that assuming there are n attributes, rename them as A1 through AN. And this is a good way because you can actually break up a long relational algebra operation into multiple steps and do the same. And or you can do the same with a row of R A1 through AN of S, like this. Both are fine. Then we said, yes? So this is kind of, I know that it is a little annoying, but you have to rename every single attribute. I mean, it's possible that some of the names are what they were before, but it's just that's, yes. That is, yes, it's supposed to be a row, sorry. Thank you. Yes?
Can you also do colon?
Yes, you can do colon equals, you can do just equals. Yes?
Can you add attributes for rename?
No, you cannot add attributes for rename, but technically there is kind of this extended projection where you basically can repeat attributes. We don't need it right now, but that's technically possible. So you cannot add, but technically you can add a column that is just a constant value, for example. All of these we will see a little bit, they're a little bit more fancy. We will just learn the simple stuff first. Okay? Yes?
So when we rename, if we do a colon equal, are we creating a new relation called R?
We are creating a new variable that points to the same relation in a way. That is called R. Oh. Yes. Yeah. So the relation is called R with those attributes, but it's like passed by reference, oh. Right? Yes. Well, it's like a logical statement, right? So you're saying that take, like you open two file pointers to the same thing. You read from this using this names and this from this using another name. So it's not like a physical copy, right? I mean, it's just logically what you get is what this is. How you implement it, that's a different question. Your implementation may make a copy, but it may not. That's like far later in the class. Yes, what else? Okay, so all of these operate in a slightly different way because they apply to the tuples as they are. The only place where you can put tuples from two separate relations side by side is by a Cartesian product. So I was answering this question online, I think. So the set operations, we ask that they have the same schema because you can technically take the union of two things that are of the same type, right? So it's like type of data object. So you can find all people who are faculty and graduate students, right? So because people have some attributes, so you can take the union of those. But if they don't have the same attributes, you don't know if they are of the same type. So you cannot take the union of all people and all buildings, right? That makes no sense. So the point of the same schema is to make sure that they are the same type of object. So, so that's why we kind of refer to the schema as a way of defining the object. And but if you want to actually compare tuples from two different relations of different types of objects, we use Cartesian product. This is where we get a little bit picky, that we want to have R and S to basically have completely different set of attributes, different names. Just so that if I say attribute A, bless you, after this, attribute A is equal to B, there's only one attribute A and one attribute B, right? So because of that, we want R and S to have completely separate attributes. So R and S have completely different attributes. Okay. Rename them if one or two of them are the same name, you have to rename them all. Okay. And then you basically get a tuple for every pair of tuples in R and S, right? So this is basically a tuple for all combination of tuples from Now remember that Cartesian product does not select any tuples. It just finds the multiplication. So Cartesian product in general is kind of useless. But as it turns out, it is necessary. You cannot just live with the joint. So the reason why is that one question I threw in there on the homework, the bonus question, that's actually a very difficult question. Okay? If you figure that out on your own, you will have seen some very interesting part. But that will require Cartesian product, not join. Okay? So Cartesian product overall looks useless, but it is in fact necessary because it gives you new expressive power. So then we learned kind of these derived operators that make life more interesting. Things like theta join or just join. It's basically a derived operator that means take the Cartesian product of R and S and then apply condition C. Now, do not abuse theta join. Okay? So theta join is only for cases where C here is what we call a joint condition. So this C condition should relate attributes from R to attributes in S. Like attribute R in A is equal to attribute B in S. If it's just about R, then it's a selection condition. So the C itself has to be a condition that compares tuples from two relations, so it should be a joint condition, where C is a joint condition. So it would be something like A1 is equal to B1, whereas A1 is an attribute in R, and this is an attribute in S, right? So not everything is a joint condition. It's not technically wrong, but if you are being proper, this is the theta joint condition should be one that is an actual joint condition. And finally, and to do theta join, you have to be able to do Cartesian product, so attributes are named differently. Okay, but because sometimes your joint condition is more complex than what the common attributes would imply. But if it is the case that all you want is to join the common attributes, what you can do is natural join. Which is basically an equality join of common attributes. Furthermore, you will not repeat the same attribute. So if there is an attribute A here and attribute A here, you will find the join that is the join of both. Then you will not repeat it. So if you had, for example, R attribute A, B, and C, and S, A, B, and D, so your natural join of R and S will be on the condition that the A is equal to A, okay, and B is equal to B, and it will give you a new schema with attributes A, B, C, and D, because you don't need to repeat the common attributes. Okay? So as many as there are attributes that are the same, it's an equality over both of them, or all of them, and then you don't repeat that.
So A, let's say you have a tuple in R that A doesn't equal tuple in S, that does not give you a new relation, or is it
right?
Not? Okay.
Well, let's do a very quick example. So let's say you have R So if I do natural join of R and S, I will have attributes A, B, and C. Bless you. And what will be in my relation? The only thing that joins from R and A is A2, right? So I will have A2, B2, and C1. Okay. Let's put another relation here, T. Okay. What is the natural join of R and S? What schema will it have? A, B, C, and E. It's like Sesame Street. Yeah, that should be a T. That makes no sense. That's right. This is, I know that before the quiz you're actually paying attention. All right. Okay. So what is in our natural join T? No, it's basically an equality join on the common attributes, which are nothing. So it's always a join is a Cartesian product followed by a selection. The selection in natural join happens to be the equality join of the common attribute. So in this case, this is going to be right. It's going to be actually the same as a Cartesian product, right? So because there is no actual selection afterwards. So so you're going to have A1, B1, D1, E1, A1, B1, D2, E2, A2, B2, D1, E1, and A2, B2, D2, E2. Okay? So remember that all joins are Cartesian product followed by a selection. Okay? So what if I had a theta join of true? My join condition is true. All are welcome. So then I would still get this, right? So that would also be the same as a Cartesian product. Okay? So remember, a join is selection after Cartesian product. Right? I will do one more simple example. Let's say I have R and S. What's the natural join of R and S? That's the only thing that is common that has the same A and B values, right? So, in this case, when they have exactly the same schema, natural join is equal to intersection, right? So in this case, this is the same result as intersection, right? So join is somewhere in between intersection and Cartesian product, depending on what your condition is, right? If your condition is a simple condition, then if your schema are the same, then it's basically an intersection. If the schema are totally different, then it's a Cartesian product. So it's kind of in between the two. It's a weird operation. Any questions?
So, for example, in the homework where we have access, like operations of projections, do you still have access to Cartesian products?
Yes. Yes. I should have written those things down. All right. I will try to clarify those. Anytime I said join, it's also a Cartesian product, which actually you do need for the book. Yes. Okay. That's a good point. Thanks. All right. So let's try to do a few things. Apparently, I still have not figured out how to use this language well. Okay. Let's do a couple of these, not all of them. So the first one asks the name of all movies that are released after 2014 and has a Marvel comic hero in them. Okay. So always think about when you're writing queries, what attributes you do need for your query, and which relations have those attributes. So the movie is made after 2014. You obviously need the movie's relation for the year, right? So you need movies and year. And that has a Marvel comic hero, so you need Marvel heroes. And, right, so this does not tell you that this hero was in a movie, and the movies don't tell me what hero is in that movie. So you actually need hero in movie. So I have to select from the movies the year. Then I need to join to find all the heroes here. So you can look at the schema. You have hero ID here, movie ID here, and movie ID here. So they have the same name, and I need an equality join, so I can use natural join. Then for these heroes that I find, I am going to join with this. Again, natural join will work because that has the same attribute. And the fact that it joins with this, like intersection, means that there is a Marvel hero, right? I don't need to do anything else. As long as it joins with a tuple here, then it satisfies my query. Okay? So, find the name of all movies that are released after 2014 and has a Marvel hero in them. So from movies, I can select that year is greater than 2014. These are all the movies made after 2014. These are all the heroes that are in that movie. Okay. Now, and then these are all heroes that are a Marvel hero. Okay. And then I want to return the name of the movie. Okay. Something like this. So check a few things. You have hero and real name. You have movie name, so I have to project on movie name. So that's easy. Okay. Now you could do the same query, okay, by doing this. So you can do movies, hero in movie, and Marvel hero, which basically is mapping. So this so far is the relation of all movies that have a Marvel hero in them, right? Now you can select from this year greater than 2014 and then project movie name. Now, you would say, well, is one more efficient than the other one? It actually really depends. That's what we're going to see later on. It depends on how these relations are stored. But ultimately, both are equal ways of doing the same query. Question, there was a question. Yes?
In that second question, is it commutative? So that is to say, can you put like perhaps in the center of sports materials and movies, asterisk, Marvel hero, asterisk, movie?
Yes, you can write them in any order, right? Because suppose I wrote this, right? So suppose I did movies, Marvel hero, right? So these have no attributes in common, right? So what you get is Cartesian product. But from this Cartesian product, you have now a hero ID and movie ID, right? When you do another join with hero in movie, you actually get the same relation, right? This will for sure be more expensive than the others. If you did that, you did the Cartesian product first. But anyway, we'll see that later. But yeah, logically it will be the same. So join is commutative and associative. Yes?
If it is advanced, you can just join
No, not logically they are the same. But when we learn SQL, we are going to talk about why some may be faster and cheaper than the other, right? For relational algebra, it's not. And actually, it's more important that you see there are many different ways to write the same thing because it's going to be part of how we do query optimization. Okay? Now, what you must not do, however, so then you can put these two here. What you must not do, which is I always see, is you should not say movies and then select, Marvel comic hero, right? Movie in something like so. That's not SQL. That's not relational algebra, right? Because this is not an attribute inside this relation. Okay, so that's the more important thing I want to see from you. And you can write it using relational algebra or theta join, but to use theta join, you have to rename them first. Oh, all right. All right, I want to do one more. And then we will do the quiz. So, find pairs of heroes who start in the same movie. So you want to find pairs of heroes who start in the same movie. Okay? And we can just, be more fancy. You can return their name, but I'm going to just return their IDs, just so that you can think about this. Okay? So think of this for 1 second. This is where it gets a little bit more tricky. But this is going to help you write correct SQL. How do you find pairs of heroes who are starred in the same movie? The only information that I have is this, right? But here, I only have a single hero, right? I can only tell that hero 3 was in M6 and hero 4 is in M6, but I cannot tell hero 3 and hero 4 are in M6 together. Right? So go through in your mind of all the operations that we have seen, think about what you would need.
If you did a Cartesian product on the same database, I think you need to do a data join and have it just that the first MID equals you have to rename it in the second MID. And then that would give you two different pair of zeros and maybe the other.
All right? So in your mind, think for a second that you need to have a comparison, but this comparison is between two tuples of the same relation. And the set operation doesn't accomplish that. Good question? Okay. So think about it and try to convince yourself that set operation will not do that. Okay? Because you actually need to compare two tuples side by side, not set of tuples with set of tuples. Okay? So this is the kind of the tricky part. So, and to be able to do that, I will have to rename the attributes so they are actually different. So I will have to I will have to create a copy. Let's call it H2 with HID2 and MID2. Okay. It's a logical copy, right? Okay. Then I took hero in movie and Cartesian product with H2. Then I'm going to select from this HID is different than HID2. Okay. So this is the SQL way of doing not equal to. Not the programming way actually does not work, or it didn't used to. We'll see. So this is, just so you get used to it. And MID is equal to MID2. Okay. I am telling that find two tuples with different hero IDs but the same movie. Okay. And then this may have more than one such tuple, right? So I need to then just project HID and HID2 to find a pair HID2 that have at least one movie in common, because it may happen that we have more than one movie in common, right? So Iron Man and Captain America are in more than one movie, but of these, that means that they have at least once starred in a movie together. Yes?
Wouldn't you have, let's say H1 and H2 were to move something together, wouldn't you have H1, H2, and H2, H1 both return twice?
Yes. Yes, indeed, that we will return both. So that's the second question. So in this case, you will have, Iron Man, Captain America, Iron Man, right? So you may or may not want that, depending on what you're going to do next. So how would I make sure that I don't return both if I don't have a preference of which order I get?
You could test to see if one's less than the other.
That's right. So you can just say, instead of not equal to, you can just say HID is greater than HID2, right? So they are integers, at least one of them is going to be greater than the other one, so if you will either return AB or BA. I'm sorry? Even if you store them as strings, lexicographic ordering, it's an ordered domain, right? And all the domains we have are ordered domains, right? Because they're all simple domains. There is nothing else. So this will always work. But probably you should not do it if they are floats. That makes no sense, but in general. So you can write the same exact query by just a join. It's the same exact deal. This is a join condition because it basically relates one attribute from one relation to the other. So now you can say like this, and then project like this. Okay? So it is important that you convince yourself you understand why that has to be this way. Okay. So, and this query cannot be written with natural join, right? Because it's not an equality join. All right, I have one more that is put right after this for a purpose. Okay. All right, so now think for again 1 second. To find the name of all movies. Okay, so the name is not yet important. You can just join later to find the name. First, find the ID of all movies that has more than one comic hero in them. Okay, think about that for a second, and then we'll write that down. So to find a movie that has more than one comic hero in them, so some of you have done SQL, written SQL, right? So your first instinct would be to say, let's count, right? Well, we cannot count. Did you see a count operation? algebra cannot count. Okay? So you cannot say the number is 3, 4, 5. You cannot do that. And that's part of the point that you cannot write SQL queries that require counting. You cannot write them in relational algebra. We will see an extension of that. But you can still answer this question, right? Yes. That's right. We actually have already found movies that have two separate heroes, right? Right? So that's what this was. If I didn't have this, this is actually movies that have at least two heroes, right? Because we have two different pairs, two different couples for the same movie but different heroes. Okay? So if I projected this, let's call this R1. If I projected this, I found all movies that have at least two or more heroes, right? It could be more than two. That's important. But it at least is two. So let's call this R2. So R2 is movies with two or more heroes. How do I find movies with exactly one hero? Subtract that from all movies, right? So I have all movies. I do know. And should I take all movies from movies database table or hero in movie? Okay. So this is the answer to this query, right? So now I'm getting more fancy. I want to find all movies that have exactly one hero. So I can find all movies so I can project movie ID from movies and subtract that too. Okay. Or I can project hero in movie and subtract R2. Are they the same? Can they be different? You don't really know the rules, but is it possible to have a movie with no heroes in them? Okay, so if you want to make sure that there's at least one hero in it, then you should use this one, right? It depends on how your database is designed. So, now if you wanted to return the name of the hero, you actually join back with movie and then project the movie name. Okay, so what you need to make sure that when you do set operations, they have the same attributes. Otherwise, set operation doesn't work. But after you do set operation, if you need to return an attribute that is not there, you can do that also. If it makes you happier, you can join before to make sure they have the same attributes, but also has the movie name. That's a little bit more, effort, which I never do, but I know some of you are going to be better at this than I am. Questions? All right, so I'm going to stop right here.